Well, it seems like it's that time of year where Calculus 2 classes in the sort of United States standard sequencing of calc are either in or just getting through all the business about applications of integrals, solids of revolution, and arc length, surface area, things like that. And browsing some of the math subreddits today, I came across a question about volumes of revolution, particularly when the axis of revolution is not one of the axes. And I was just working with somebody on this last week. And yeah, I figured I would put this out there in case it helps anybody else. So I'm going to take a look here at a generic setup to this problem. And this is going to be a story about using the method of cylindrical shells, but this, call it a trick. It's not a trick, it's clever thinking. Or if we want to use the modern parlance, wherever you do something tricky for something or clever for something, you call it a hack. So we have hacked the method of cylindrical shells here. How about that? That makes it sound good. Okay, there's also the method of discs or washers, but we're going to do a cylindrical shells problem because it matches the question I saw earlier today. So the generic setup for finding a volume of a solid of revolution using the method of cylindrical shells is that you have a function f of x, you clip it here and here on the x-axis, and then you revolve that around the y-axis. The volume that you end up generating is calculated with this integral from a to b, 2 pi x f of x dx. Let me make sure I'm on my right page here. Yeah, there we go. This particular formula is a little weirder than the discs or washers formula, but you still can remember it if you recognize that the thing that you're integrating, the thing that you are accumulating many values of, is 2 pi rh, except you're writing r, the distance from the y-axis, the x-coordinate, and h, the height of the function at any one point. You're writing 2 pi rh as 2 pi x f of x, and you have to remember where you've seen 2 pi rh before. Well, that's the surface area of a cylinder. And so you have to think about, well, why in the world would you accumulate infinitely many areas of cylinders to produce a net total volume? Well, the answer to that is if you think about a bunch of stacking cups that little 2-year-olds play with, right? You have a series of 10 stacking cups. There's the skinny one and the bigger one and the bigger one and the bigger one. Each one of them has an area, 2 pi rh. But when you stack them all together, what do you have? You have a solid volume constructed out of all these stacking cups. So that's how this works in a very, very rough sense. Okay. Now, what happens when we switch the problem up? And so I have a lousy diagram here, I admit. I have just some function f of x here from x equals a to x equals b, and it's getting revolved around the y-axis, and it's creating a terribly drawn solid of revolution. Integral of 2 pi x f of x dx, right? That's what we would use. Now, what if we want instead to take that same piece of function and the area under it and revolve it around something that wasn't the y-axis itself? Because that's what the formula before is engineered to do, is to revolve something around the y-axis specifically. Okay, so the slide has already given away the gimmick a little bit, but the story is maybe we don't want to revolve around the y-axis, which is x equals 0. Maybe we want to revolve around a different vertical line, some other x equals L. So there's two options. One option is you have a deep understanding of how this original integral was built, and you go back and you reassemble it for a different axis of revolution from the ground up. Option number 2 is change the problem. That's the hack, right? We're hacking the method of cylindrical shells. What you do is you figure out, well, what would I have to revolve around the y-axis to get the same volume as this new problem I have? Okay, and so when I go back to my lousy drawing here, if I want to move this blue curve and the area under it around the line x equals -1, if I just pick up the axis of revolution and this function with its two endpoints and just pick it up, move it over by 1 unit and drop it down, I would now be revolving around the y-axis again, right? So that's what we are going to do. Here's my new page. What I've done here is taken the previous badly drawn f of x. It was between a and b, and I've picked it up, dropped it down. So now my endpoints are a plus 1 and b plus 1. This blue function is the translated version of the original f of x, and now we'd be revolving around the y-axis. And so maybe this problem puts us a little bit more back in our comfort zone for using that integral formula. All we really have to do, the worst part of this, is if we had the function f of x that gave us this original blue curve before we translated it, how do we move a function left or right by a certain number of units? Well, that's what you might remember from algebra when you learned about translation of functions, right? To move a function up and down, you just take the whole function and add a constant to it. Positive constant moves it up, negative constant drops it down. If you want to move left or right, you have to go find every instance of x and either add or subtract c, okay? To move to the right by 1 unit, we trade f of x for f of x minus 1 or x minus c in general, okay? So it's kind of counterintuitive that to move to the right, which we would normally consider positive, that we end up subtracting this number. But what we're doing is we're relocating important features, right? If the original version of the function gave a good version at x equals 3, but then we picked up the whole graph and moved it to the right by 1 unit, we would have to there go to x equals 4, so that when we do x minus 1, we're back at an input value of 3 to locate that same important feature. That is why that translation works that way. So that's what we're going to do. So here's a sample problem. We're going to find the volume that's generated when x squared minus 5x plus 6 is revolved around x equals negative 3. Now, how do we draw this? Well, I made this up so it's easily decrypted. This is a parabola. It can factor as x minus 2, x minus 3, I hope. And the roots, therefore, are x equals 2 and x equals 3. And so this little hoop of the parabola down below the x-axis is the piece of the parabola we're interested in. So it's the parabola between the x-axis. So starting at x equals 2, going to x equals 3, that region, and then we want that to go around x equals negative 3. And I just realized I drew this end badly because that should be going all the way over. There's 5 units of difference between the left endpoint of our function and the axis of revolution. So my little dashes showing the swooping around, they should be way the heck to the left of the visible part of the screen. But it's too late, and I'm not going to go back and redraw it. These drawings are terrible. They're not going to help anyway, right? Okay, so our job is to either consider this problem from the ground up and think about how the integral is constructed from partitions and accumulating a whole bunch of 2 pi RH's, but expressing that in the language of the variable x and the function, or we cheat and we recognize that if we just take the entire setup here, pick it up, and move it to the right by 3 units and set it back down, now we have a problem that'll generate exactly the same volume, except we're revolving around the y-axis. So let's take our function f of x and let's translate it 3 units to the right. Well, there it is. Every instance of x is just replaced by x minus 3. The left endpoints, or the left endpoint, which was originally x equals 2, now bumps up to 5. The right endpoint, which was 3, now bumps up to 6. The axis of revolution that used to be x equals negative 3 has now bumped up to the y-axis, and I dropped my mouse too far down and it activated that little bar at the bottom of my Camtasia screen. Now it's gone. Okay, so we're cheating, but we're still going to get the right volume. So the original problem again, find the volume generated when our function x squared minus 5x plus 6 on the interval from x equals 2 to x equals 3 was revolved around x equals negative 3. And we said, ooh, that's gross. We don't want to revolve around that line. We would prefer to revolve around the y-axis so that we just have a straightforward use of that volume formula. And so we just take it all, pick it up, move it over by 3 units, set it back down. The axis is now the y-axis. The endpoints of 2 and 3 have become 5 and 6, and this function becomes its translated version. And so the updated problem is to find the volume generated when this translated function on the interval from 5 to 6 is now, this is the important part, revolved around the y-axis. And so that's the integral we have to solve. The integral from 5 to 6, 2 pi x f of x. I'm not going to evaluate this integral. This is just multiplying out, doing some power rules, throwing in the limits and subtracting, right? So that's the easy part. It's the building it up is the hard part. So I don't have a final number, but the number that this returns will be the volume that was requested by the original problem. This trick, this clever thinking through the process works for washers and discs as well. Again, the main story is if you're revolving around something that you don't want to revolve around, pick up the whole problem, move it, drop it back down so that you're revolving around something you would like to revolve around instead. So if you're doing, say, a discs or washers problem and, those, y equals square root of x squared minus 7x plus 9, whatever it is, and you're revolving that around the x-axis, that's easy. That's the integral of pi times f of x squared between the appropriate limits. But let's say you wanted to revolve that around x equals 2 instead. Okay, well, that line is up here, and that's a horizontal, y equals 2. That would be a horizontal line. You say, yuck, I would rather revolve around the x-axis. So in that problem, you take the axis, you take the function, you pick it up, you drop it down by 2 units and snap it into place. So you have a slightly different function because it's been translated, but you're now revolving around the x-axis and the volume is going to be exactly the same. Okay, so you can use this for both scenarios. I hope that helps a little bit. I've talked way too long and now the dogs are barking. They have a magic skill of knowing the 10 or 15 minutes a day where I'm trying to talk into a microphone. It's always when they start barking. So yeah, there you go.